Hello everyone. So in this session of Unit 4, we will look at a very useful and a very prominent technique of verification, which is called equivalence checking or formal verification. So formal verification is a very general class of is a group of methodologies that is used to. So formal techniques are a group of methods that are used to verify or design in one way or the other. So equivalence checking is one part of formal verification that we will look at. There are other formal verification techniques. One is called assertion-based verification. I think there are one or two more types of formal verification techniques. So equivalence checking is a part of formal verification, is a type of formal verification. So we'll look at that in detail. I'll introduce the topic and then we will compare it with the regular dynamic verification, that is the stimulus based verification, and static timing analysis both. We'll see how equivalence checking, where does it lie in the ASIC design flow and how is it useful, what is its uniqueness. We will look at the application where and what all places can we apply it. Then we will look at the formality flow. Formality is a tool from Synopsys. So we will take that formality as an example and I'll go through the formality flow. There is one more tool called one more very famous tool called conformal LEC, which is from Sweden, and both tools are very good for formal verification. When you work in your labs or in your industry, whatever tool you have access to, you can work on that. If you understand the formality flow, the conformal flow is not so different from it. Although the commands are different, but the flow wise they both are same. And then we look at the summary. So the definition of formal verification is that we are looking at the logic equivalence check. So for the scope of this course, even for the industry wise, you can safely say that formal verification and logic equivalence checking, these two terms are used interchangeably. So although formal verification is a much more generic term, but logic equivalence checking and formal verification, they go hand in hand. The idea is that it verifies the logic equivalence. So formal verification is a process which always needs two designs. On one side, the design can be on both the sides, the design can be in either RTL form or netlist form, and it tries to compare these two designs for functional equivalence. So it works at the Boolean level, in the sense that it will only check the Boolean equivalence. It has no way, there is no scope of checking the timing verification, or there is no need to give any symbol. So one side there is a design which you consider to be golden. It can be either RTL or netlist. On the other hand, you again have a design which is either RTL or netlist, and formal verification can verify whether both of them are functionally equivalent or not. Right? Even some of the tools can even work on functional level. So the advantages, does not test functional correctness. It's an advantage in the sense that usually what happens in a dynamic simulation is that let's say you are verifying a simple FSM, then in dynamic verification you need to give some vectors and make sure that all these states are covered, all possible use cases are covered, to make sure that your design is functionally correct. Now, formal verification does not need any kind of stimulus, so it does not need any test vectors, and it is very fast when compared to dynamic simulation. It will only generate functional vectors when it finds out that one side the design is called golden, other side or reference, other side it's called implementation. So let's differentiate the two terms. The golden or the reference design is the design which you consider to be correct, and you are verifying the implementation design against this design. So reference will be your reference literally, and implementation is something you want to verify. So once you have, how the flow works? First, you have to obviously, so it does not replace dynamic simulation obviously, because in the first place the RTL has to be verified with some kind of vector, whether it be random or be specific or whatever, or deterministic, whatever. There has to be some testing that has to verify that the RTL matches the specification, right? Nothing, neither STA nor formal verification is trying to replace that. But once you have the design with you, once you are satisfied that yes, my RTL is correct, then all other versions of this RTL can be verified against the reference. What could be that version? That could be synthesized netlist, or that could be a post layout netlist, and the process of verification is comparatively faster. So let's say, okay, let's go forward and see the ASIC design flow and see where the formality lies. So one more example here is that since formal verification is aimed at comparing the Boolean equivalence, comparing the functional equivalence, it can even compare netlists in different technologies and different hierarchical structures. For example, let's say you have one design which is synthesized in one particular technology, let's say Artisan 130 nanometer, and on the other hand, let's say you have a design which is having a different clock frequency, but it is synthesized with Artisan 180 nanometer, for example. So the base design is same for both these netlists, but the frequency and the technology, they both are different. Now the formality, since it works at a functional level, it can compare these two netlists and tell you whether they are functionally equivalent or not. There is no timing check, so frequencies of not of any consideration. Even if the hierarchy in one of the netlists is different than the RTL hierarchy, or whatever the hierarchy is in the golden netlist or RTL, it can still verify it. So that's the advantage. It doesn't depend on hierarchy, or doesn't depend on what type of cells are used for implementing the netlist. The only thing it needs is that it needs the functionality of each and every library cell that is used. Obviously, you will have the dot-lib. So in the case on the left hand side, for the Artisan 130 nanometer case, you already have 130 nanometer library that you will read in the tool. Here in this case, you will have to read the 180 nanometer library in the tool. This way, it knows the functionality of each and every standard cell, and now it can verify whether this netlist on the left hand side is equivalent to this netlist. Right? So always remember, there is one golden design and there is one implementation design, or golden or reference, or on the other hand, there is always an implementation design. So this is the typical ASIC design flow, and how do we insert formal? We'll see how do we insert formal verification into it. How is formal verification now becoming the de facto standard for comparing RTL versus netlist and netlist versus netlist? So first thing, you have the RTL design. Now the RTL design has to be checked using some kind of stimulus. So it's not that the stimulus, the dynamic verification is gone, but no, yes, there will be some kind of dynamic verification here to make sure that RTL meets the specification. Now let's say the design, the RTL meets the specification, but now some other guy tells you, your manager tells you that yes, the RTL is functionally correct, but the coding style is bad, or you have to make sure you have to rename some signals you have to follow good coding styles, or you have to change some hierarchy, right? But the functionality is still the same. You are not changing the functionality, but you are improving the readability of your code. Maybe you are improving the logical partitioning of your code, and so on. You can work on the RTL, and now you can use formality. You can use formal verification tool like formality to make sure that the new RTL here, the modified RTL now matches the RTL that passed your stimulus, right? Without, now let's say if the RTL is of a medium size design, the process here, of checking whether they are logically equivalent or not through formality or NEC will take about an hour or so. For a even smaller design, it will take still quicker. It will be still shorter. For a decent size design, it might take even an hour. That's it, or a few hours, not more than that. For a decent, a big design, let's say, the dynamic verification can take up to few days. Complete dynamic verification, running all the tests. But on the same design, running formality between RTL and the modified RTL will take maximum up to 2 or 3 hours, right? Depending on the size of the technology that we and so on. But that's the max. I mean, formality runs of more than a few hours are not. It means that you are running on a very big and complex design. Usually, formality runs are of duration of 3 to 4 hours for a decent size design. So that's your runtime saving on. You don't need to run all the test case on the modified RTL. You can just run formality and be done with it. Again, then now this modified RTL we will take it through synthesis, which is a normal process for getting a netlist, and then let's say now in synthesis, now you want to verify whether the design is synthesized correctly. This is not to verify whether the tool has problems, whether the synthesis tool has problems. Although, yes, in some cases the synthesis tool might have a problem, might have a bug, and you might discover this bug during formality. But the idea is here is to make sure that your synthesis constraints are correct. What if by mistake you set a logic 0 on an input port? If you set logic 0 on an input port, DC will optimize all the logic related to that, related to whatever input port that input port is driving. DC will remove that logic completely, and now you can discover such problems in formality. Many a time the DC scripts are long and the constraints are long and it's not easy to debug them, but such cases can be easily caught by formality. Or you have set some variable in synthesis which optimizes off your registers, some of the registers. Then also formality can point you out that I cannot find these registers in the netlist, what I was able to find in the RTL. So all such things, all such problems that might have crept in because of user input can be caught by formal equivalence. So this is the idea. First idea is, first you can do synthesis, you can do formality between RTL RTL. Next step is you can do between RTL and netlist. And third, now the synthesis goes through a lot of, the synthesized netlist goes through a lot of changes in backend, in PNR, during PNR. There is clock tree synthesis, there is placement, there is routing, and there are so many things that go on. So the best tool to make sure that there is no logic change when you go from synthesis to post layout netlist is formal equivalence. So you are making sure that your backend flow is good and it is not introducing any design change. At every step, usually in the industry, at every step that modifies a netlist in any manner, usually formality is run, or some kind of formal equivalence is done to make sure that there is no design change. This is the de facto standard nowadays in industry, right? So the bottom line is that make sure that no logical changes are made. That is the bottom line. So once you do dynamic verification here at the first stage, after that all these stages you don't need any sort of similar. You can verify everything using formality. So if you look at the post layout netlist, so post PNR netlist, let's say now at PNR netlist, ideally you would want to check that the functionality is correct. We check it using formal equivalence by making sure that this netlist is equivalent to gate level synthesized netlist. You already make sure that synthesized netlist is already equivalent to RTL. So A is equal to B, B is equal to C, and A is equal to C. The timing you check using STA. So at the post layout stage, a tool, STA tool like prime time, and a formal equivalence tool like formality Using both of them, you can make sure that your design is good for sign off from both functional and timing perspective. This is why these two tools are very necessary now to sign off any chip. Right? So let's look at the flow. So equivalence checking is a branch of static verification. What does static verification mean? Again, static verification means that any vectors are not applied. It is independent of any vectors. It employs formal mathematical techniques to make sure a designs are equivalent. It proves two versions of the design are or are not equivalent. The flow is read in the design, match. Matching has to go, the matching process makes sure that so there is something called a compare point, we will look at it afterwards. It makes sure that all the compare points are matched between the two designs, the reference and the implementation. Only after matching has completed, it verifies. So this is the part, verification is the part where it will compare the logic. And then if let's say you have any register or any output which is showing as functionally not equivalent, then the tool also provides you ways to debug the problem. Right? Matching and verification stages are the most important. Those are most impacted by design transformation. We'll look at what design transformations are. So we'll now going ahead. All our discussion will be focused on one tool, that is Synopsys formality. I'll be using the material from Synopsys University courseware, and again all the concepts here discussed here are also applicable to any other formal equivalence tool. So formality is an equivalence checking solution that uses static techniques. We have already seen that. It supports all out of the box DC ultra optimization. So now compile ultra or DC ultra is very aggressive in terms of optimization. We have seen that. It employs few techniques that change the design in some manner, and you might have problems when doing formal verification. So one such example, for example, we will look at first. Let's look at compare points. Then I'll give you examples of the cases where some of the DC ultra optimizations tend to cause problems, right? But there is a communication channel between design compiler and formality, using which design compiler can tell formality, okay, I did this aggressive change. Now formality knows that such a change has taken place. It will help you to make sure that it's functionally equivalent. It supports verification of power up and power down states. Formality supports low voltage, low power flow, multi voltage flow. Multi voltage flow has a lot more complexities when compared to single voltage flow. So the low power multi voltage flow adds a lot of additional cells during synthesis. They can be level shifter cells or retention cells, for example. In that case, you'll have to make sure that the addition of these retention cells or the level shifter cells do not modify the functionality, right? So it supports that. Formality supports that. Formality. So the implementation of Synopsys, the group of Synopsys tools that aid in the design implementation. The platform is called Galaxy platform, which includes design compiler for synthesis, IC compiler for PNR, and formality for formal equivalence. So formality is part of the Galaxy platform from Synopsys. So capabilities, these are a couple of marketing slides which tell the capabilities of formality. Exhaustive verification without test vectors, we've seen that. Verification of all design compiler default optimizations. So this is a very important thing here. Now what happens is that if you are using, as an engineer, I am using, let's say I am using a third party tool. I am using a tool which is not formality, but I am using design compiler, compile ultra command. Now let's consider a case where I want to do retiming. Now what retiming does, it will move the flops around and in the combination logic cloud. So it will. So you have a flop. We saw an example in the detailed representation that the flops are placed at logical boundaries in RT. But let's say if we have violations if we have violations in synthesis, then DC can move these flops around for you to borrow some timing slack from the next or the earlier stage which has positive slack. Now the problem with retiming is that although at the port level the designs are functionally equivalent, but if you consider flops, the deep enough flops, the deep enough flop in the RTL is now not equivalent to the deep enough the retime flop in the netlist. And formality checks and any equivalence tool, it will check the functionality at each and every flop data point. So in this case, using a third-party tool, a tool which does not understand retiming, the 2 points will be not equivalent. They will be not functionally equivalent. Why? Because in the RTL, the data pin of the particular flop has some other value, but in netlist, because of the retiming, because of the movement of combination logic, the functionality is different. Now, what many engineers would do if they cannot pass the formal equivalence between RTL and the netlist, engineers tend to avoid such optimization steps. I have also done that in my career. Is that we tend to avoid such aggressive optimization steps which are difficult to verify using any formal equivalence tool. So it is very, very important to have a good formal equivalence tool that will help you make sure that all aggressive optimization techniques such as those applied by DC alpha, like retiming is very popular nowadays, like retiming or sequential output conversion. All these aggressive techniques they can be verified by a formal equivalence tool. This is where formality is very strong. This is where the leader tools, the industry leading tools like formality and conformality are very strong about. They are able to verify even the most complex optimization techniques by design compiler, right? So it mentions here it proves functional correctness of register retiming, complex data path, phase inversion. So the compiler tries as the switch where it by default it will try and optimize the design by inverting your sequential output. The output of the register, it can invert it and see if it can aid into more optimization, low power implementation. So a lot of advanced features formality supports. Then if you're short on the compute resources, you can use the distribution verification technique and split the load across different CPUs using formality. It has since it's very tightly integrated with design compiler. The formality helps you in reducing the user setup with the automated guidance functionality, where it helps you using automated guidance. You can very quickly set up formality. You don't need to write your own commands. It has a good GUI. So a GUI in formality is very, very good. It helps a lot in debugging. Then it has some log. It has all the language support that you need. System Verilog, VHDL, Verilog, and formality also includes a tool called ESP. So there was a tool called ESP-CV earlier, which Synopsys bought. This tool can even work at transistor level. We will not go into this. It's outside the scope of this course. It's a very, very unique tool, and the application is again it addresses a very niche segment where it addresses the segment like memories, full custom memories, where memories are built separately, they are not synthesized. But the code is written for simulation, which is called a behavioral code, and you want to make sure that the behavioral code in fact matches the netlist of the memory. So the netlist of the memory in this case is a transistor level netlist, and this tool is able to verify that. It is able to verify whether the behavioral model, which is written separately, is it functionally equivalent to the transistor level memory netlist. So this is one example of ESP-CV. It's good to know that such a tool exists. When if you will go into industry and you work on full custom design, then it's a good tool to try. Now this is again a marketing slide. Is that it tells us that formality is algorithms are they are pretty good at doing the fast verification. They are good on performance side. They are less compute intensive and so on. It has a lot of tool optimization techniques. A lot of DC's tool optimization, design optimization techniques like resource sharing, retiming, register merging, or register inversion are easily verified. So yeah, this figure is a very good figure which tells what all can be targeted by formality. So whatever digital design you have, complete synthesis based design like logic. This logic here means it's a design RTL design that is synthesized. Again, data path is nothing but an RTL which has a lot of, let's say, adders and multipliers. Only that the full custom part, that is the RAM, ROM, and any other full custom logic, this part can be verified by ESP, formality ESP. As I told you before, it compares the behavioral model against the transistor level netlist. Now let's look at the key concepts of formality. So on one hand, you have the reference of the golden design. This design is the golden design against which formality tests for equivalence, and it is assumed that it passed functional verification. Obviously, formality has only the engineer has to make sure that the design passed functional verification before calling it golden. On the other hand, you have the implementation design. This is the modified design. This is derived from reference usually, and it is the modified design, whether it be a modified RTL or a synthesized netlist or a planar netlist. So one example here is the gate level implementation, which is the synthesized netlist. Then there is a term called containers used by formality. A container is a self-contained space into which formality will be the design. Now formality reads two designs: reference design and implementation design. So for reference design, formality will form a reference container. For implementation design, it will form an implementation container. So you have different containers for reference and implementation. Apart from the designs, the containers also contain the library. Let's say you are reading RTL. While reading RTL, you might not need a standard cell library. Why? Because RTL, if your RTL does not contain any uninstantiated cells, then in all probability you will not need standard cell libraries. So the reference design will only contain the RTL. Reference container will only contain the RTL design. But the implementation container now will contain a netlist, synthesized netlist, plus also the standard cell libraries that are used to synthesize the design. So a container is just a superset which can contain the design, plus it can also contain the library. So this is the ASIC verification flow using formality. So again, RTL is verified functionally using functional simulation. It goes through synthesis using DC Ultra. You get the netlist. First level of formality you do between RTL and netlist. Netlist goes to IC compiler for backend. Now you also do the formality between the post layout netlist and the synthesized netlist. You can also do formality between the post layout netlist and RTL, but it is recommended to do the formality as shown here. Why? Because in terms of naming conventions and structure, the synthesized netlist is more closer to the post layout netlist when compared to RTL. So if the two designs are structurally similar, it will take less time for formality to verify. Since you've already verified that RTL matches with the synthesized netlist, for post layout netlist, use the gate level netlist and synthesized netlist as golden. Don't use the RTL. You can use the RTL, but probably you will have to make more of an effort to verify the design. So this is the idea behind formality: design A, design B. Any design process that modifies the design, whether it be RTL or netlist, formality can check the equivalency for you. After formality proves the equivalence, the implementation design. So this is what I've been saying here is that after formality proves the equivalence of the design, implementation design to a known reference, now this implementation design can be established. So for RTL to netlist, RTL to synthesize netlist, this is the reference design and this is the implementation design. But for netlist to netlist, now this becomes the reference design and this becomes the implementation design. It is logical, of course. Once you have R is equal to I is equal to R. This is a logical inference, right? Now let's look at the formal verification component. So similar to the way prime time breaks or design compiler breaks your design into timing parts, formality will break the design into compare points. What are the compare points? Compare points are the design nodes at which the functionality is compared. It is the primary output, register internal registers, that means the D pin of the register, the PK pin of the register, and so on. Inputs of black boxes. We'll see what black boxes are. Nets driven by multiple drivers. So these are the compare points. That means at all of these formality when it comes to RTL to gate level formality or even netlist to netlist formality, what goes through most restructuring is the combination of. You can understand that. Let's talk about RTL, the synthesis process. Synthesis process will quickly map, first elaborate process itself. It will map your registers to GTEC registers. It will map your combination logic to GTEC components. And during optimization, if you don't consider retiming and sequential output conversion, it will make sure that the logic cone, the functionality at the D pin of a register between RTL and netlist remains same, and it will optimize among that combination logic. That is the most optimization. The sequential optimization for most of the cases will remove the register if it is not used or if it's constant. But apart from retiming and sequential output conversion, it will not change the functionality at the input of the register ever. This is why any formal verification technique, the compare points are the registers, pins, primary outputs, inputs of black boxes. Black boxes are such modules or components for which formality does not know the functionality, or we tell formality that don't worry about what is inside. So we set them as black box. By setting something as black box, we are telling formality to make sure to verify the functionality at the input pins of the black box, like memories. Nets driven by multiple drivers. We see that. Logic cone is a term used for a group of combination logic, for a combinational cloud that drives a compare point. We will see some figures that will elaborate this point. So two things are important here: compare point and the logic cone. So let's see this figure. Now during the read process, reference and implementation designs are automatically segmented into manageable sections. Why? It has to divide the design into manageable sections to verify the functionality. It cannot read in the complete design and make sure that all the outputs are equivalent. It cannot do that. It's not possible from CPU resources point of view or from algorithm point of view. So it breaks it into chunks of logic, which it calls logic cones. So logic cones are group of logic bordered by registers, ports, or black boxes. The output border of a logic cone is known as a compare point. So let's say in this case, what formality did is, so let's go back here. Let's see, there is some logic here also. Now it started with an input port and goes through the combinational cloud and hits the first DFF it sees. This on the left side is a logic cone. So this part here is the logic cone, and the compare point is this DFF. Now it again starts at the output of the DFF and traverses through combination logic and hits, let's say, hits the black box input pin. For this compare point, the black box input pin, now this is the logic cone. Any logic that is coming via any input port or any black box output pin or any clocked output pin, all this cloud forms the logic cone for this particular compare point, right? So this is the way that, and please note, it can have the effect of multiple inputs, right? This, for example, this black box input here is being affected by this DFF, it is being affected by this input port, it is being affected by this input port, again this black box, and so on, right? So it is sort of at every compare point there will be a cloud of combination logic that is being fed by a number of flip-flops or input ports or black box output ports. This total cloud of combination logic is known as a logic cone. Now, so in the reference design, both in the reference design and the implementation design, formality will break the design into logic cones and compare points, and now it will try and match the name of the compare points in reference versus the name of the compare point in implementation. Why this matching is required? Let's say synthesis, for example. Synthesis changes names. We have seen that the register names are changed. If you ungroup any module, then the hierarchy will be different. Again, the name will be changed. So, lot of design processes like synthesis or PNR, so PNR usually doesn't change the instance name. These processes, lot of times, will ungroup some hierarchy or maybe form a separate group or change all such processes that change. Some of them change the hierarchy of an instance, some of them will change the instance name. This is the reason why formality should first know. So you have to compare. You have a compare point in RTL and you have a compare point in netlist. Now it needs, let's say there are 1000 compare points in RTL, and let's say there are again a number of compare points in netlist. Each compare point in RTL should be first matched to a compare point in the netlist before you can make sure that logic cone is equivalent. First you need to make sure that the name matches. This process is called matching. Both non-function name-based and function-based matching methods are deployed to map compare points. Even if you change the name completely by using the change name command or something with DP, formality will still try to match the name using some functional algorithm. So the name matching, the name-based matching is called non-functional matching. The function-based matching, there are some algorithms. They are based on the functionality of the compare point, right? So the matching cycle is very important before the comparison takes place. Then comes the verification cycle. After the logic cones have been matched, after the compare points have been matched, the next step is to make sure that the logic cones are equivalent. There are many algorithms that are used by formality. I think this BTD is binary decision tree. ATPG algorithm, we know it's automatic test setup generation. I'm not sure what SAT is, but there are a lot of algorithms. There are a lot of papers published on this. You can probably go through them using using the site before or something like this. So you can read up this material. But formality uses a bunch of these algorithms to make sure that the cones are functionally equivalent. Then comes the debug cycle. Once the verification step is completed, the tool will generate a vector. It will generate a number of vectors that will prove that both the cones are not equivalent. They are not functionally same. For example, here, let's say you have a problem in the design and they are not equivalent. It will generate a vector like this. It will add all the input conditions here. For example, it can be input port or DF. It will port some value, and it will show you that at the compare point the values are different. Let's say in this case the value is 0 and 1, so they are different. So it will give you a vector also, so that you can verify that where is the problem, right? The logic cones can be huge. For a data path, usually the logic cones are very big, and it's not easy to to point out the problem unless and until you have a vector. So vector helps a lot. So this is the flow. Environment setup. This is the place where you set the variables. There are variables which control a lot of things in formality. You set those variables. You create containers by reading the design. You first create the container, then load a libraries and design into a particular container. There are two containers. One is reference. One is implementation. So you read the reference design into reference container. You read the implementation design into implementation container. You use run verify. Verify will first do matching and then run verification, view results, and then if you find any non-equivalent points, you debug. Right? This is the formality flow. So formality interfaces, library interfaces. Formality can read Verilog also. It can read lib synthesis library. It can read even system Verilog or VSDL. Or the formality ESP can even be SPICE, right? So for standard cells, let's say you are using the .lib for synthesis, you can use the same .lib for formality also, because formality again has to match for any tool. Even if you are doing simulation at a gate level netlist, you will need to read the standard cell library Verilog model. Here you can read the Verilog model. Also, you can read the .lib. You can read any one of them, because both of them have functionality and formality understand both. For guided setup, it needs a formality guide file called SVF. So I haven't used VSDC, but I use SVF, so I'll explain this. So DC Ultra employs a lot of optimization techniques, or it will many times change names for registers and for some nets. So DC Ultra can write out an SVF file, a formality guide file, which lists down all this information, and this can be read by formality to understand the design better, right? The outputs are failing patterns. For failure cases, it will write out the vectors. Formality reports, it lists down all the compare points that are non-equivalent, whatever are equivalent. You can save a session just like prime time and design compiler. You can then restore the session and debug more. You can save the containers also for future use, and these are the platforms supported. So this is the formality window. So a formality window is a tab-based interface. For example, there are tabs for reference, implementation, then there is debug, then there is verify, and so on. And it again supports a tickle command interface, which is same as what is supported by design compiler and prime time. So guided setup is a very interesting feature which is very useful if you are working with Compile Ultra. Usually it is not needed with Compile because Compile doesn't do that many aggressive optimizations. So now formality can account for synthesis optimizations through the use of a guided setup file automatically generated by DC Ultra. So there are some commands you set SVF file name and so on. When the Compile Ultra starts working on optimization, it will write out this information of optimization in this container, in this file. It's a binary file. It includes information about name changes, register merging. Now name change although might not be important because formality will be able to match the compare points without even the name change, but register merging is very important. Why? Because register merging will reduce the registers. It will so for example, if two or more registers are merged together, the number of registers in implementation now will be fewer than the ones present in RTM. So register merging is very important. Again, multiply architecture, right? Now if you go through designer documentation, you will find that Adders and multipliers are of two kinds. The first is the non-pipeline, that means it is 100% combination logic. The second ones have pipeline inside them. Now this pipeline is not fixed at a particular place. So when DC, let's say you are reading a pipeline multiplier in your RTL, DC will use this multiplier and then it will shift the pipeline according to the timing constraint. That means if the depending on, let's say you have a single pipeline, depending on whether the timing violation is on the left hand side of this pipeline or the right hand side of this pipeline, and depending on the slack available on the other side, it will move this pipeline. This is very similar to register retiming. Such cases are very difficult. If you do not give any guidance to formality, then they are difficult to verify because compare points now have different logic codes. RTL has a different logic code, netlist has a different logic code. So these transformations are Compile Ultra will write something about these transformations in the SVF file. So this way, formality based on the guided setup, formality can use most efficient algorithms during matching and verification, and it improves performance. Over and above that, it reduces the headache of debugging such complex failures. Now in case of retiming, if the retiming occurs, if you have enabled retiming, then if you are not reading SVF file, certainly there will be an equivalence failure. Now in that case, if you debug that, now retiming happens for the case where the combination logic is too much, right? Then only retiming will happen. Retiming is there to solve the timing problem majorly. And when is the timing problem? Mostly when there is a big combination logic, and when there is a big combination logic, the logic code will be very big. So debugging such problems, such logic codes are huge, and it will take you days to debug the problem if you do not use guided setup. So this is where guided setup is very useful. It's a very useful feature of formality. That's what it says, right? Required when verifying a netlist containing retiming or register optimizations. SVF is most important when you have retiming enabled. So how do we use the automated setup file? You use this command set SVF. You tell what name in design compiler. So DC will automatically write out the SVF file for you, and to use that, you set this variable in formality to true, and you give the path of this. This file.svf is written by, so file.svf is an output from design compiler, guided setup is an output from design compiler, and for formality it's an input. Now when you load the designs, it supports these many formats. For all practical purposes, you would be probably using Verilog, so you would be using read Verilog or read Verilog. During read command, you have to give -r or -I to tell formality what is this? Is this a reference design or the implementation design? Right? Now this is the read design process flow. Read Verilog, -r means reference. Read DB, this is the standard cell library. And then now set the top level design. Whether you are reading multiple RTL files or you are reading a single netlist file that has multiple modules, either you set the top yourself, the top level design name, or you set the -auto. -auto formality will automatically find out what is the top level design name and it will set it. It is very important before switching from reference to implementation. This step is very important. Set top. Again, you read the implementation. The only thing that changes is the -I option. You read the same library if you are using the same library across both the designs. Again, set top. So read technology, read reference, set top, read technology again, read implementation, set the top level. If your RTL does not use any cell from the technology library, this step is optional only when the reference design is RTL and does not use any hand instantiated cell. Right? You might be using memory, so here you will also read the memory D. Right? Next, so these are the commands. Read design file, read verilog, read db, set top. These are the commands. Again, pure RTL does not require any component library. Now, in the let me show you. So in the GUI, as soon as you read reference, the reference would be, if it's read correctly and the top level is set correctly, there will be a green mark appearing here showing you that you have read the reference correctly. Same thing goes for implementation. So these buttons here will tell you at what step you are flow wise and whether that step has gone correctly or not. So implementation design, you read it like this, you give the -I option. This is the warning here, do not read the implementation design until having specified the set top command. Right. Okay, these reference and implementation design are ready for equivalence checking here because there's tick mark at both the places. We move ahead. Then we perform the setup. So setup is used to speed up verification and prevent from unexpected failure. Now, if you are not using Synopsys Auto Setup, then you might have to. There are a lot of variables like design compiler, a lot of variables in formality which control so see formality when it compares between RTL and netlist, it needs to internally synthesize RTL itself, right? Because it needs to compare, it also needs to understand all the synthesis constructs to make sure that the Boolean function of the RTL matches the Boolean function of the netlist. When in case of them not being functionally equivalent, two compare points not being functionally equivalent, it will show you the logic cone, and in the logic cone it will show you the gates on the RTL side as well. So it is internally synthesizing. Although the idea is not to get the lower area like design compile. So the formality synthesis engine is just aimed at providing a gate level representation, not optimized for either timing or area. It is just for showing you the functionality. So the synthesis engine inside formality is entirely different from the synthesis engine inside design compiler. But there are variables which control some kind of functionality. For example, there is one variable which controls the value of the registers at initialization. Now these variables you might have to tweak before you can get the setup ready. So you will have to spend some time in setup to understand, to make sure that the verification goes on fine. And this is an iterative process. It might happen that you did not initialize, you did not set the correct value of some variable, you go and you find a lot of compare failures. Then you find, okay, like I missed setting this value. So you go back again to the setup part, set the particular variable, and then again go and verify again. For example, clock gating. Now clock gating, the step in synthesis will add a latch and an AND gate or an integrated clock gating cell. Now this integrated clock gating cell is extra, right? Now in RTL, the enable pin gating is on data pin, not on clock. But in the netlist, as a result of clock gating, the gating part shifts to clock from the data pin, right? So now the compare points are not equivalent. If you compare the clock connection or the data connection for this clock, they are not equivalent from RTL to netlist because of the clock gating. Now you can take care of this in the setup. In the setup you can say that I have clock gating in my design. So please make sure that all such cases of clock gating are verified properly. So there is one variable which controls that. So this is the part of setup. Best thing you can do is you can use Synopsys Auto Setup to prove. So this will read the SVF and read the synthesis options and prepare the setup for you. This is the quickest thing you could do. Now, black boxes represent the logic whose function is unknown. It can also contain logic, but you don't want to verify it. One example is memory, a very famous example. Now, memory is you will read Verilog 5's behavioral model or .lib for memory. You do not want formality to go inside a memory. Let's say there's a memory, it's a full custom design, there are transistors inside. You don't want to go inside this memory, but you want to make sure that the logic driving the input of this memory is verified. So formality for any black box, whether implicit or explicit, formality will make a compare point at the input of the black box and it will verify that, right? So black boxes are commonly used for blocks that are not synthesizable, but you need some kind of model for that, either .lib without the function attribute or an empty Verilog module where you only define the ports. So formality needs to know what are the inputs and outputs for this black box, right, to make the compare points. So you need to give the port definition. This port definition can come from a .lib or from a Verilog module. So how do we mark a design as a black box? This is the variable. So I was talking about variable. This is the variable which says that whenever formality encounters any unresolved reference, it will make it a black box. So for example, let's say you are using a cell, and for cell you did not keep the address. Now it is unresolved. So formality will make that a black box. This is not recommended. Why? Because now for this kind of a black box, empty design is fine, because empty design at least tells formality what is the input and the output port. But a black box will not tell formality whether the ports on the design in the instance of Verilog netlist, whether they are input or output, right? So it's a good practice for if you have a black box but you don't have a definition, it is a good practice to make an empty design and read in the formality. So it will make it a black box. Second thing you can do is that you can use this command set SQL interface only, the set variable, and set it to mark cells which you want to be explicitly black box. Or you can use this command set black box. So you can use there are multiple ways to set something as black box. Then there's a problem of matching the compare points. So as I told before verification, before comparing the logic codes, formality needs to match the compare points between reference and netlist. So it follows following algorithm in a given order. It will go for exact name matching. Obviously that's the most straightforward technique. If you do not have any name change between reference and implementation, then exact names will match for compare points. So it will go for name based. Then it will go for name filtering. This is again name based. Name filtering is not exact name matching, but let's say if case is changed or if any underscore is added, like it happens for registers, then it goes for topological equivalence. We will see what topological equivalence is. Signature analysis, we'll see what it is. Then compare point name matching based on net names. This is again name based, but it is based on net names, not the compare names themselves. So when it matches, it will give you a pop-up box that matching is completed, and it will tell you how many points are matched and how many points are not matched. So exact name matching, it will map exact case sensitive, case insensitive. Both come under the category of exact name matching. For example, if reference is like this, capital A, B, capital C, and if the implementation has small a and c, it will still match. It will not have any problems. You don't need to do anything extra. Name filtering, there's a variable which has name match filter characteristics. Many times these will add underscore, or it will add if you ungroup it will add underscore. For example, see this example. Reference has a slash here, which means that it has a separate hierarchy, but implementation does not have a slash, which means that DC has ungrouped it, whether explicitly or implicitly. So it will add an underscore here. It will add an underscore here also. So the default value is this. All these characters are filtered for name match. So a slash is filtered and it is matched to underscore using name filtering. So it is capable of doing that. Again, you don't have to do anything special. Then comes the topological name matching. So it will. So first, the name filtering and exact name matching techniques are used, and in most of the cases, almost more than 90% of the compare points will be matched. Because again, design compiler or any other synthesis tool, they don't use arbitrary name changing. They don't do arbitrary name changing unless and until you do something special, right? Then formality attempts to match the remaining compare points by topological equivalence. What it means is that If now it will start comparing, it will know, okay, it will know that okay, these two compare points might be matched. There is some suspicion, so it will start comparing the logic codes. And if the logic codes are topologically equivalent, that means they have similar structures, it will match them. Again, so matches can also be made to either directly attached. So if the net name is same across the implementation and reference, and if it sees a compare point driven by a particular net which is the same name, it will try to match. Next comes the signature analysis. The last comes the signature analysis. This is a slightly more complex thing. Now, a signature of a compare point is an iterative analysis. So it is the way the logic code behaves on giving some input vector. So that is the signature. So they are a functional signature that derive from random pattern simulation. So it will input some random patterns. And so the difference is that functional signatures are derived from random patterns. Topological signatures are derived from span and cone topology. So the second case here, the topological case compares the logic codes by structure. The functional signatures compare the logic codes by input by giving some random patterns and looking at the signature at the functional values in the logic code. Signature analysis, since it involves giving vectors, internally generating vectors, it is only useful if the number of mismatches are less. If you have thousands of compare point mismatches, and if you try to run signature analysis, it will take a lot of amount of time, right? It will be time waste. So what people do is they will set signature analysis false to start with, and then later if they find few cases where signature analysis can be turned on, they turn it on. Right? So this was all about matching. You don't need to know all of this to start working on formality. Only because when you run matching and you run verify, you will see all these methods like turning signature analysis on and so on. So it's good to know that such things happen. Otherwise, if you give the basic automated setup, if you use that, you don't need to give any special command to aid matching. Right? Formality will do the matching for you. Yes, there might be some points which are not matched. In that case, only in the case where the matching is not complete, you can read more about it. But if you are using compile ultra, and if you are using formality, and if you are using SPF, in most of the cases you will not need to do anything special. Right? Now comes the verification. The command to run is verify, and after the verify is run, formality will give you a list of compare points, and it will categorize them as succeeded. That means the logic codes are equivalent. Failed means logic codes are not equivalent. Inconclusive means that formality cannot conclusively say whether they are equivalent. It does not have any vector to verify they are non-equivalent, nor does it say conclusively they are equivalent. This happens when there are data paths are very complex, or the logic code is very big, right? And the algorithm runs out of time. So this is the report, a typical verification report. Match compare points, passing, failing. Here it is categorizing the compare point as black box pin, loop, black box net, cut point. Let's not go into this. Port, DFF. These are most important. The important ones are black box pin, port, DFF, and latch. It tells that there are total 2 latches which are not equivalent. What is not compared? Constant registers are not compared, which is expected. Constant registers are more. So now if we are doing RTL versus netlist, and design compiler would have optimized of the constant register. So the register that is optimized of during synthesis will be still present in the RTL, in the reference design, but that register will be absent. So obviously it will not be compared. Don't verify is something which you might have set as not verify. We can set some points as don't verify. Unread are not verified by default and do not affect any other thing. Unread are something which is here. What is unread? Okay, latches are unread. Yeah. Let's see further. So verification is incremental. It can continue again after being stopped. You can stop verification after, let's say, some point of time. and then you can say verify minus restart. You can even verify a single compare point by giving the option. You can verify a compare point. There's a lot of flexibility in verify command. You can even set some command as some point as don't verify. Then let's look at the status messages. Passing means that two compare points are functionally equivalent. Failing means that they are not equivalent and formality would have generated a vector for you to verify. Aborted means that it cannot conclusively say whether they are equivalent or non-equivalent. Maybe because compare point is too difficult to verify. The logic cone is huge. Unverified, it represents a point which has not been verified yet. Not verified or not run if there is some error that prevented verification from running on that point. So you need to debug this more. Right. Now let's come to debugging. Obviously, debugging only makes sense once you have some experience in running formality, but these slides will help you in future also. So in case equivalence checking fails, formality has a command called diagnose. So there are two main verification results that require debugging. One is failing, other is aborting. If something failed, or if any point is aborted, that means it is not conclusively equivalent. Then you can say debug. You can switch on the diagnose command and help formality debug it. So this is the flow chart. You run diagnosis on failing points. If the problem is identified, first choose the point to debug, display pattern window, display logic code, isolate the difference. Let's see it in the GUI. I think we also have a GUI. Okay, let's move it. Yeah. When a verification reports that design is not equivalent, the failure can be due to an incorrect setup also, like the clock gating part I told you. So in case you have not done anything special for clock gating, formality will report a number of latches as being extra, not matched, plus all the flops that are affected by clock gating, it will report as not equivalent. This does not mean that design is not equivalent. This means that there is some problem in setup, or you can even have a genuine logical difference. You have to check and warnings and information messages in the log file. This is very important before you debug the failures. Check the transcript window, that means the window, the TCL window in the GUI for black boxes or for simulation or synthesis mismatch. This is very important, simulation synthesis mismatch. We have seen that in RTL coding, if you don't do good RTL coding, you can have a simulation and synthesis mismatch, and such a mismatch can also affect the formality. Check for unmatched compare points. Any unmatched compare points can also lead to a failure, compare failure. So you have to resolve, or you should know that the compare points, what are the unmatched compare points, whether they affect the failing compare points or not. Check whether SCF guidance file is read successfully. So these are the basic steps you do before even going on to the debugging of an individual failing point. Right? Now you can have these states where you have large number of unmatched points. If you have large number of unmatched points, you should not actually verify. You should first resolve this. Now when you have very small number of unmatched points, which is usually in an expected design, so what will be unmatched will be some constant registers, clock gating latches, they will always come as unmatched. So if the number of unmatched points are small, then you need to look at whether there are only small number of failing points and small number of aborted points. If such is the case, then there can be a genuine logical difference. If there are large number of aborted points, then you might have a setup problem, right? If you have no failing point and some aborted points, it points to a very complex circuit or combination loops. So mostly when you are doing formality for the first time without any experience, you will face this type of cases. Secondly, you might face these type of cases where there are any setup issues, right? Usually, if the version of design compiler is stable and the formality version is stable, it is being used by different groups, different design groups in your team, or then first debug the setup features. First debug the variables, what you have set the variables to be. Debug that you have set it correctly for clock gating. You have read correctly the SVF file. So debug all such things first before going on to the logic code itself. And when you have verified that your setup is correct and you have small number of failures and you suspect that it could be due to genuine logical difference, then you go to the diagnose part. So analyze point command examines the failing point. You can say analyze point all, and it will generate a list of suspect causes in setup, right? Or it will tell you that there is a problem. It can tell you whether there is a problem in setup, or it can tell you whether there is a genuine logical failure. So analyze point will help you in diagnosing the failures further. So this is a debug window. It shows you the failing points. So it is telling you that on the left hand side it's reference, right hand side is implementation, the type is DFF. Now you isolate a failing point, right click on that and set diagnose. So there is a separate analyze tab will appear. You select the error candidate and then you can say show me the logic code. It will show you the logic code like this. You can select the analyze selected. You can select one failing point, say analyze selected. It will open up the logic code for you. Logic code it will give you, as you see, debugging logic code is not an easy job. A big logic code. It will tell you where is the mismatch. So it is telling me here that at the data pin here, there is a mismatch. There is a 0 and there is a 1. The 0 and 1 comes from a vector that formality generates for you. So pattern viewer apply pattern feature is used to diagnose. You can say right click and say show patterns. It will show you the reference and implemented design input side by side together with input patterns which cause the outputs to be unequal. This is the vector that formality generates to prove that the logic codes are not equivalent. So again you can use the features in the GUI to debug it further. So this is a pattern window. Now this is a very interesting part where it shows you that reference is affected by this. These are the pins affecting the reference input cone. These are the pins affecting the implementation cone. They can be different. In many cases these can be different. If these the left hand side, this side and this side are different, you have to first debug that. If they are equal or so. In case you have a clock gating, in case the left hand side is RTL, right hand side is replaced, and you have a clock gating, you will have some extra entries here, which is okay to have. So the point I am trying to make is that the left hand side and right hand side can be different, and the differences can lead to failures, or they can also not lead to failures in the cases where you are able to explain the differences, right? So the differences can be due to clock gating, they can be due to scan insertion. But you have to be first very sure that these differences are not causing the failure. On this side you get the pattern, the input vector that causes the failure. Here it is telling you that reference design is loading 1, implementation design is loading 0. It will tell you the state of synchronous data, this is the input data, the clock and synchronous load if the pin is there. One constant which means they are both same, so you don't have to worry about this. You have to worry about the synchronous data which is different. And this is the vector 1 and 2, there are 2 vectors that prove that design is functionally not equal, right? Obviously this will only make sense once you start working on formality. But again it's good to know these things beforehand, and when you start running formality you'll probably recall what we did before. You can fix the design. Once you fix the design you will have to run the formality again, and it will say formality succeeded, failing non-equivalent is 0 0. Everything is 0, right? So this was all about formality. So we discussed the importance of formal equivalence in the ASIC design flow. We saw the ASIC design flow and we saw that formality is very essential to make sure that the ASIC design flow you are not any synthesis flow or any PNR flow or any RTL modification flow is not causing any functional disturbance. So it is, so formality is essential. I'm underlining the word essential. Any chip design team in the industry, every chip designing team uses formality, and there are many unique uses of formality, right? So these two tools are very they are the industry leading tools for formal verification. Many times requires design understanding for efficient debug. This is the problem. So as an ST engineer or as a synthesis engineer, usually synthesis engineers are most comfortable with formality because the setup is the same, right? But many times you will have to go back to designer and get him fix his RTL or get him help you understand the formality non-equivalences, right? So the tool is essential. I mean, any logic equivalence tool in your flow, you can have one, either cadence LEC or synopsis formality. But it is essential. It is most effective while doing ECOs. What are ECOs? So ECOs are something. Now let's say you have done synthesis. Now let's say you have a design, a decent size, a big design will take about a day for synthesis, about few days more for making sure that all the synthesis reports are correct. It will go through post layout, the backend flow. The backend flow will take multiple days. It will take 4, 5, 6, 7 days to get the routing completed, and then the backend engineer plus the front end engineer, they both will start fixing the timing using some tool or some flow, and then they will be, in some more days they will be very close to sign off. But now let's say, and during all this time period, functional verification will keep going on. Functional verification is never complete. The fact is that functional verification is rarely complete. And then there might be some specification change, or there might be some new bug that you discover, and that requires an RTL change. Now what do? If you start from synthesis again, you will take 2 to 3 weeks to again come to the state where you are now. That means to come to a state which is close to sign off. Is it desirable? No. What it means is that if a change is simple enough, let's say if the change is adding an AND gate, ANDing 2 signals, then you change the RTL on one hand, and then you modify the post layout netlist on the other hand. You don't do synthesis. You modify the post layout on netlist on one hand. This is called engineering change. This is called an ECO. Formal verification is the best way to verify this. There is no other good way in fact. You do a formality between the ECO netlist and the updated RTL to make sure that the engineering change you did in the RTL and in the netlist is functionally equivalent. Formality is most effective in such cases. People add complete logic like adders and FSM in functional ECO, and in those cases, formal equivalence formality, a tool like formality is essential to verify that. The idea is, the bottom line is that any process that leads to design change, you have a golden design, and any process that leads to a change in its functionality, formality will help you with that. Whether it is being between RTL and netlist, or whether it is being between netlist and netlist. So please go ahead, try out formality. It's a very interesting tool, and it is most essential in ASIC design. Thank you.